Okay, so let's start our discussion with synchronous motor. Now, synchronous motor is a modified version of three-phase induction motor. Three-phase induction motor, but the difference is synchronous motor is not self-starting. Not self-starting. It's similar to single phase. It cannot start. It's not self-starting. So how do you start it? Okay, that is one question. So another thing is here, as you see, this is your rotating magnetic field. The rotating magnetic field is revolving at a speed that we call synchronous speed. And in case of a three-phase induction motor, the rotor speed, that is the speed of the rotor, is less than the synchronous speed. However, in case of synchronous motor, the rotor rotates at the same speed of the synchronous speed. So the speed of the rotor and the speed of the magnetic field, that is the rotating magnetic field, is synchronized. Okay, these two are synchronized. That is why it is called a synchronous motor. So in case of a synchronous motor, your NR, that is the rotor speed, is equals to your synchronous speed, ns. Okay, now the question is, how do we start a synchronous motor? Okay, the first thing we do is that we start as a three-phase induction motor. Start as induction motor. Same principle. Start it as three-phase induction motor. Okay, so when you start a three-phase induction motor, the rotor will start to rotate and at a time, after some time, the rotor will achieve a speed that is NR, that is not equal but very close to the synchronous speed. Okay. So once it reaches that kind of point, we have to do something so that the NR jumps to NS. Okay. So how do we do that? So to do that, there is something that is called damper winding. Damper winding. Damper winding is provided in the rotor. Okay. This will actually help achieving the synchronism. How do you do it? We provide a DC excitation. DC excitation. Previously, we did not use any kind of DC excitation, but in case of a synchronous motor, there is additional DC field connected to the rotor. Okay, this is the DC excitation. The current that will be flowing from the DC excitation is called the field current. Okay, IF, that is the field current. This DC excitation, you can think of it like this way, that this DC excitation, once this rotor is rotating very close to synchronous speed, to turn on this power source, this DC excitation, it gets energized. It provides a force, some additional force, to push it towards the synchronism. Okay, to push it just enough so that it reaches the synchronism. And once this is the north pole, say for example north pole, and this is the south pole, once they get interlocked, the south pole and magnetic south pole and north pole gets interlocked, it will keep rotating in the synchronous speed. Okay. You just need to push it that far so that they can actually interlock between themselves. Then it will achieve synchronism and it will keep rotating in that synchronous speed. Okay. So so this is the basic procedure to start a synchronous motor. The point and the next point is, once you actually provide this kind of synchronism, it will keep rotating in the synchronous speed. And if you keep increasing the load, the synchronism will not break. It will keep rotating in the same speed. That is the synchronous speed of the motor. Okay. So you can say synchronous motor is a constant speed motor. Okay. Now there is one thing. So you are increasing the load. Okay. The NS is always fixed. That comes from the supply side, and NR is also fixed in case of a synchronous motor. So what will be the effect of the load on the speed on the synchronous motor? If you try to visualize it like this way, say for example here is your NS and this is your NR. Okay, so in normal scenario, say for example in no load scenario, think of it like this way. This is the rotor and this is the stator. This is the stator and this is the rotor. They are interlocked. South pole and north pole are interlocked, and this is, say for example, the line of action. Okay, this is the middle line. Okay, once you increase the load, the rotor will keep rotate, but the distance between the two there will be a distance created between the stator magnetic field and the rotor. So it will be something. So this is your stator, so for example, and this is your rotor. Okay. So initially this is your line, this was the middle line here, and this is the middle line here. So there is this gap, created. Okay, a kind of delay, and that is called delta. Okay, this delta is called torque angle. This is called torque angle. That means when there is a load difference, if you keep increasing the load, there is going to be a distance between the RMF, that is the synchronous motor, that is RMF, and the rotor. There is going to be some distance. A delta will be created, that is the torque angle. If you keep increasing the load, this torque angle will increase. Okay, so as the load is increasing, the torque angle is increasing. Okay, but the rotor will keep revolving in the same speed, that is ns. It is revolving in ns, the rotor will keep rotating in the same speed, that is ns, but there is a distance will be created. Okay, now if you keep increasing the load, there will be a time, that is, you can say, that is the pull out torque. Okay. The load is too much that it can no longer stay in synchronism, so the delta is too much, that is delta is too large. Then the synchronism will break and the motor will come to a steady state, motor will stop. Okay, so you have to ensure that the load is not so much that it actually comes to that point, it does not go to that point. Okay, this is one thing. Next, let's look at the equivalent circuit of synchronous motor. So in the stator side, you are supplying the power, three-phase power, that is Vs. I am drawing here single phase, for a single phase. Okay. And this is your stator, this is the Vs supply you are providing. The current you are providing, that is your armature current, Ia. This is the armature resistance. Okay. And this is the reactance. Okay. And this will provide, and the rotor side, this is something that is called Eb. What is Eb? It is the voltage generated in the stator winding by the synchronously revolving magnetic field at the rotor side. So this is my plus, this is my minus, this is going to oppose this Vs. Okay, and this difference, this voltage here, you can name it as ER, the resultant. Okay, so the ER is equals to V minus Eb. Okay, Eb is created in the rotor. Okay. Eb is created in the stator by the rotor magnetic field. Okay, so this is going to oppose the voltage supply. You are providing this in the stator side, this is going to oppose the stator. So this is happening in the stator winding. This is happening in the stator circuit, not in the rotor circuit. This is your stator circuit. Okay. And then what about the rotor circuit? What about the rotor circuit? In the rotor side, you only have a winding. You only have a winding. And you are providing a DC excitation here. And this is your field current, IF. And it is providing the flux. Okay. And as you can see, this one and this one is not connected, because in your motor, stator and rotor is not connected. There is a air gap between the two. Okay. So this is your equivalent circuit of your your synchronous motor. Okay. So now let's look at the vector diagram of your synchronous motor. First, this point. This is your V. This is your V by Vs, that is the supply voltage. Okay. Now, in case of no load, theoretically theoretically the V and EB, let's just place it here. Okay, this is your EB. So this is your EB. Theoretically, when there is no load, the delta should be 0. Okay, that here delta is equal to 0 degree, no degree and no distance. This delta, no distance here, no distance here. So what will be your ER? ER will be something like this, somewhere there in this side. This is your ER. Okay, that is the resultant EMF. Now this is the theoretical version. So you have your supply voltage, you have your EV, and this is your ER. So what will happen when there is load in the loaded condition? So let's come here again. First, this is your V. This is your V. In case of load, it will be something like this. The EV will be something like this. Okay. So this is your EB. Okay, this is your EB. Now, if you remember from your HSC, we can draw. Here is the vector summation between these two. Okay, so we can draw something like this way. We can draw something like this, a parallelogram, and this one, this line here, this line here, this one is your ER, that is your resultant EMF. Okay, and what about the current? What about the armature current? Again, this is happening here. This is your VS. Okay, this is your EB and this is your ER. And what will be the distance between IA and what will be the phase difference between these two? As you can see, there is this reactive component and there is this reactance. Resistive component and reactive component. Now the RA is normally very small compared to XS. So you can think of it like a reactive, completely reactive. So if it is inductive, completely inductive, the phase angle should be 90 degree. Okay, so if you can measure, you can just using like this way, you can draw like this. Okay, so this one will be your IA, that is your armature current. Okay, so let's finish up the list of the things. Okay, now first of all, so there is your 4 basic component. Now this one, this angle is your delta, that is the torque angle. Okay, what about this? This is your supply voltage and this is your armature current. So that angle between these two is your theta, and your theta is your power factor angle. This is your power factor angle. Okay, so in general scenario, in normal scenario, the IA is lagging the supply voltage. So it is, since it is inductive, it is lagging. Power factor is less than 1. Okay. Now, if you look at the this portion here, this is your IA cos theta. Okay, and this portion here, this is your IA sin theta, right? Okay. Achha. In the next lecture, we'll actually see how in case of a synchronous motor, how these parameters actually changed based on your supply voltage or your supplied field. Okay.